Hi, Doc Revis here. In this video, I will show you how to use Graham's law to carry out calculations involving diffusion and effusion of gases. We show the equations involved in Graham's law calculations on this slide. The middle equation is the first one I want to bring your attention to. It is Graham's law that involves the relationship of the rates and the relationship of the time to the molar mass. And note that the molar mass has a square root equation associated with it. In a formal sense, diffusion is considered when we consider overall rates. Effusion, in a formal sense, is considered when we consider the time. However, in many texts and in many conversations, effusion tends to be used more than diffusion. So how do we differentiate them? In a diffusion calculation, you will use the rates. And note that R1 is diagonal to its molar mass. And note that R2 is diagonal to its molar mass. A tip on when to use this one. When you hear terms like rate or rates, or you hear speed, or the problem is talking about how fast, or you hear some indication of relative rates, then you would use the R1 over R2 equals square root of molar mass 2 over molar mass 1. In the case of effusion, Graham's law, on the far right side of this slide, we note that T2 and molar mass 2 are both in the numerator, and T1 and molar mass 1 are in the denominator. Now, keep in mind, by the rules of math, we can actually flip or invert any of these equations. So, how do you know when to use the effusion equation involving time? When you hear clear indications of time, or passage of time, or how long did it take, then you would use this form of Graham's law equation for effusion. So again, you use the rate R equation when there are indicators of rates, speed, or relative rates. You use the T2 over T1 equation when the problem involves simple passage of time, or how long did it take to cross the barrier. Perhaps the best way to understand this is by working some problems. Here's a problem. A gas made up of only carbon and hydrogen is found to effuse through a porous barrier in 1.5 minutes. Under the same conditions of temperature and pressure, it takes an equal volume of bromine vapor, 4.73 minutes, to effuse through the same barrier. Calculate the molar mass of an unknown gas and suggest what the gas might be. Notice here that there is simply a passage of time, therefore we use the T2 over T1 equation. Keep in mind that in some texts you will find that the term effusion is used to describe all of the transport of the gases, including when they are formally diffusion. So keep that in mind. So it's very important that you note whether or not the question involves a passage of time or it involves a rate. So the first thing we'll do is mark up this problem with the variables. And we find that we have a T2, which is an unknown, and a T1, which is known at 4.73. Now, you could actually assign T1 and T2 either way. However, it is important in working these problems that you establish your own standard. My standard always uses T1 as the known and T2 as the unknown. Okay? So, we also see that we're looking for the unknown molar mass. Therefore, this is clearly a Graham's effusion problem. We have passage of time, so we're going to use T2 over T1 equals square root of M2 over M1. We take the values, We plug those values in, and we solve the problem by using standard math rules. So we have 1.50 minutes as T2 over the standard bromine 4.73 minutes, and this equals the square root of M2, which is the unknown, divided by the standard molar mass of bromine of 159.8 gram per mole. We rearrange the equation to solve for M2 using standard math principles, and we obtain 16.1 gram per mole. That is the molar mass of the unknown gas. Now, to find out what gas this might be, we use trial and error. So, we know that it's composed of carbon and hydrogen. So we use a combination of carbon and hydrogen, and we arrange it so that we obtain a molar mass of 16 gram per mole using 1 carbon and 4 hydrogens. And we know that CH4 is methane. Let's work another problem. It takes 243 seconds for 4.46 times 10 to the minus 5 moles of xenon to effuse through a tiny hole. Under the same conditions, how long will it take 4.46 times 10 to the minus 5 moles of neon to effuse? We know that this is clearly an effusion problem because it's passage of time. Therefore, we use the T2 over T1 form of Graham's law equals square root of molar mass 2 over molar mass 1. We plug in the values and we leave T neon as our unknown. Again, my habit is to use T1 as a standard. So we have the standard on the bottom of 243 seconds equals square root of the known molar mass for neon at 20.2 gram per mole divided by the known molar mass for xenon at 131.3 gram per mole. We then take the math and we simplify it, and the entire expression on the right hand of this equation equals 0.392. We take that value, 0.392, times 243 seconds, and we get an answer for T of neon of 95.3 seconds. So again, when the problem involves passage of time or some indicator that is clearly effusion, you use the T2 over T1 equals square root of M2 over M1 equation. So let's work another problem. And in this case, we're going to examine diffusion. An unknown gas effuses 1.66 times more rapidly than carbon dioxide. What is the molar mass of the unknown gas? Can you guess its identity? Note in this question we use the same term we said it effuses. However, 1.66 times is an indicator of a rate. So in this case, since it's a rate, we will use R1 over R2, even though in the problem it states effusion. Note that some authors choose to use effusion even when it's formally diffusion, and we wanted to point that out to you in this problem. Others would have chosen to use the term diffusion. So let's read the problem again. An unknown gas effuses, actually it diffuses, at 1.66 times more rapidly, indication of a rate than carbon dioxide. What is the molar mass of the unknown gas? Can you guess its identity? By the rules of math, since the unknown is 1.66, then that means that carbon dioxide equals 1. So in other words, when you have a rate such as this, the other value is always 1. So this is 1.66 compared to 1. So it's 1.66 the rate for the unknown compared to a rate of 1 for carbon dioxide. With that in mind, we simply take Graham's diffusion equation, which relates R1 over R2 to square root of M2 over M1. We put in the values of 1 for the rate of carbon dioxide divided by 1.66 as the rate for the unknown. And note here, they're unitless, and that's okay because they will actually cancel out. But it is the ratio that is important. That ratio is equal to the square root of M2, our unknown molar mass, divided by the known molar mass of carbon dioxide of 44.0 gram per mole. We would then use standard math practices to get to our answer, and we find that M2 equals 44.0 divided by 1.66 squared equals 16.0 gram per mole. And 16 gram per mole, if we want to guess the gas, it's methane, because we can take 1 carbon and 4 hydrogens and obtain a molar mass of 16 gram per mole. So again, although the problem reads and uses the term effusion, we know that the problem is carried out as a diffusion because it involves a rate. So when there's a rate involved, we use the R1 over R2 equals square root of M2 over M1 form of Graham's law. Let's work another problem. How much faster does hydrogen escape through a porous container than sulfur dioxide? This is clearly a classical R1 over R2 equals square root of M2 over M1 Graham's law of diffusion, where hydrogen is our unknown and sulfur dioxide is our known. So, since hydrogen is an unknown, we call it X, and therefore sulfur dioxide is 1 as our standard. So if we take the 1 as our standard, R1, and we divide by X, which is for H2, we set that equal to the square root of the respective molar masses of 2 for hydrogen and 64 for sulfur dioxide. We then do standard math here. We basically flip it to make the math a little bit easier for us. And we obtain X equals to 64.06 divided by 2.016, square root thereof equals 5.634. And so what we discover is that the rate of hydrogen is 5.634 times the rate of sulfur dioxide. So in the case of clear diffusion, you simply use the rate expression of the Graham's law and you will obtain your answer. So there you have it, how to carry out Graham's law equations for diffusion and effusion. Keep in mind that the terms diffusion and effusion can be confusing in some texts.